Good morning or good afternoon, sixth period and fifth period. Uh, for you, it is Tuesday, February 2nd, and we're doing partial fractions today. I'm actually recording this on Saturday morning. We did integration by parts yesterday, and so I have this integration by parts warm up, and we'll do one more example from the integration by parts notes before we move into partial fractions. Also, as a note, as I previously said, in yesterday's video, I said the wrong day for the assessment. Your next assessment is going to be on the Tuesday the 16th. Your next test is on Tuesday the 23rd. And if you have any questions over topic 6.10, integration by parts or partial fractions from today, feel free to ask. And I'll try to include some of those homework problems if you ask on Thursday or Friday's videos. Okay. First off, for this warm-up, we have this table of values of f prime, g, and g prime, and they give us that the definite integral from 0 to 1 of f prime times g is 5. And we are asked to figure out the integral from 0 to 1 of f times g prime. F times g prime. Well, anytime we see an integral of a product of two things, that should indicate integration by parts if u sub does not, normal u sub does not work. And it wouldn't work here. These are two completely different functions. We don't really even know what functions they are. So normal u substitution won't work. But we have a product of two things, so it's probably u substitution. And so when it, no, not u sub, it's probably integration by parts. And as a reminder, integration by parts is the integral of u dv minus, no, equals u times v minus the integral of v du. And so we need to identify the different pieces of this. We need to identify the different pieces. And so this is the integral we are wanting to find. So it's probably this piece, because that's what we don't know. That's what we're asked to find. And so which one would be the u? Which one would be the dv? Well, dv indicates that it's the derivative of something. U, we would need to take its derivative. And for dv, we need to choose something that we can find its integral. And if we chose dv to be f, we don't know the antiderivative of f. They didn't give that to us here. They gave us f, f prime, g, and g prime. And so whatever we choose for dv, we have to be able to integrate it. And I can't integrate f because I don't know its antiderivative. But I can integrate g prime because the antiderivative of g prime would just be g. So we're going to have g prime of x dx, it's going to be our dv. And then the f of x, it is our u. And if that's the case, well, let's write this down with our table. That would mean u is going to be f, and we're going to find du, got to find v, and we have dv. dv we just said is g prime times g prime dx, and then the antiderivative of g prime would just be g. The derivative of f is f prime. And so now if we write out what would come next, it's going to equal u times v, so that would mean f times g, evaluated from 0 to 1 minus the integral of v du. V du. So g f prime. I'm going to put in order f prime g because that's how they wrote that over there. The integral from 0 to 1 of f prime g of x dx. Well, This entire integral over here, integral from 0 to 1 of f prime g, they told us that it's 5. Awesome, we know that piece. And then the integral from then f prime g, that's already a completed part. That is an antiderivative part that we now just need to evaluate at the upper and lower limits of 1 and 0. So that will end up being f of 1 g of 1 minus f of 0 g of 0, then minus the 5 from that integral. So f of 1 g of 1, that's 4 times 3, minus f of 0 g of 0, 2 times negative 8, and 2 times negative 4, which gives us negative 8. Minus 5. So 12, and then that ends up being a negative 8. So 12, actually plus 8 then. So 12 plus 8, that's going to be 20. 20 minus 5 will give us 15. So the answer is E, 15. Okay, well, that was the warm-up. This was on the 2008 exam. Let's move on to the notes. As I said in yesterday's video, we're going to first finish up with the last question. With example 12 in integration by parts. So we introduced tabular method when we did number 11, and the same thing is happening here on number 12. And anytime we're doing the tabular method, we want to choose, we're going to make 3 columns like we did on number 11, signs that will start with positive and alternate, u column that we take the derivative of over and over again, which means the thing we choose to be u needs to eventually get to 0, so it's going to be the polynomial part, and then the dv will be the other piece that we're going to take the integral of. Yeah. So dv u signs positive, and then so here our x cubed, that'll be the u, and the e to the negative 2x dx, that's the dv. So x cubed, and then e to the negative 2x dx, and then that'll be negative 3x squared, and then we take the integral of this, so we need to divide by the derivative of that power. So negative 1/2 e to the negative 2x, and then the positive, take the derivative again, that'll be 6x, got to divide by the derivative of the power again, so it'll be positive 1/4 e to the negative 2x. The negative root of 6, divide by the power again, derivative of the power, so negative 1/8 e to the negative 2x, and positive, that'll now be 0, divide by the derivative of the power again, and so that'll now be negative 1/16, or not negative, positive this time, e to the negative 2x. Yeah, why won't it stay focused? There we go. Okay, and then as I demonstrated yesterday, now just to write it all out, we start with the sign, we go straight across, then diagonal down. So the first term will be, so it'll equal x cubed, and the times the negative 1/2 e to the negative 2x. So I'm going to actually put a negative in front, over 2 e to the negative 2x. And then again, it will start with the sign, go straight across, then diagonally down. So it'll be minus 3x squared over 4e to the negative 2x. Then again, Start with the sign, go straight across, diagonal down. So that'll be a negative 6x over 8 e to the negative 2x. Then start with the sign, go straight across, diagonal down. It'll be negative 6 over 16 e to the negative 2x. And lastly, the plus c. Okay, well, that was that last example. And now we're going to move on to partial fractions. Partial fractions. So, integration with partial fractions. And to introduce what that is, instead of having things being multiplied, now we're going to have polynomials being divided. And we've seen that a lot already. We saw that in topic 6.10 when we're doing long division, when we're doing the inverse trig problems with completing the square. And so this time we're going to have polynomials being divided. And this particular one, though, we can do with u substitution. I mean, we would choose the bottom to be u, then du with I guess they should have had a plus 1 there. Du would have ended up being 2x plus 10 dx. If you just multiply the numerator by 2, or really divide this du by 2, then it would work out to just being 1/2 integral. It would end up working out to be, I'll write it up here. It would work out to end up being 1/2 integral of 1 over u du is what would end up happening. And then integral of 1 over u du is natural log of the absolute value of u. So 1/2 natural log of the absolute value of the denominator. And so that one's not bad. But if that 5 in the numerator was practically any other constant, then this would not be as easy and would not work through u substitution. Because suppose if we had something like this, 8x plus 82 over x squared plus 3x minus 10. If we tried u substitution with the bottom being u, the derivative of that u is 2x plus 3 dx. There's nothing I can multiply 2x plus 3 to end up getting 8x plus 82. That's just not going to work. So at that point, it might seem like it's not integratable, or at least not by stuff that we've learned so far. So the goal of this lesson, we are going to transform a rational expression into a sum of relatively simple partial fractions. We're going to transform a rational expression into a sum of relatively simple partial fractions, which then those new ones are easily integratable. And when I say partial fractions, what I mean is we're going to start with a polynomial over a polynomial, and we're going to transform that polynomial over polynomial into being something that's a constant over a linear function plus a constant over linear over and over. Another way to write what this will end up being is we are going to how do I want to word this? Well, this process, it's always going to end up where we have a linear in the denominator. It's going to end up where we have a linear in the denominator. There's other ways that can end up happening, but where you have repeating linear terms in the denominator, we won't see that on the BC exam. You also wouldn't see that. There would be more common in Cal 3 or differential equations. So the idea is we're going to end up with non-repeating linear factors in the denominator. We'll end up with non-repeating linear factors in the denominator. Anything more complicated than that in the denominator would be in higher level math classes. This method will be used for when you have a quotient of polynomials like this. When you have a quotient of polynomials, and that it can be factored into non-repeating linear fractions. So a key idea of what's going to happen is we're going to start off with some f of x over g of x, like they have over here, polynomial over polynomial. And we're going to essentially just use algebra operation of polynomial over polynomial. No, move that out of the way real quick. Still keep that down there. And so when we split this up into partial fractions, it's going to end up becoming where we're going to have a constant over some linear expression plus another constant over some, I'm just going to put cx plus d. And then there could end up being more. There could end up being more. But this is the gist of what's going to end up happening. And this makes it a whole lot simpler, because now if I was to try to integrate this, we started off with this left side. We want to integrate that left side, but we can't as it currently is. So we're going to split that polynomial over polynomial into a over ax plus b over cx plus d plus, then there could end up being more terms than that. Usually not tons. And so the idea is we would now want to integrate that. Well, if we're now integrating this, the capital A, the capital B, those are essentially just constants being multiplied. And so that A would still end up being multiplied. And so we have 1 over ax plus b. 1 over ax plus b. Well, you could do u sub with that, and you would have called the denominator u. And we would have ended up having to divide by the derivative of the denominator. Well, derivative of the denominator is going to be that little a. And then it would have ended up being 1 over a integral of 1 over u du, which would just give us natural log of the absolute value of that denominator. So natural log of the absolute value of ax plus b. And then the same thing would end up happening on this one. It would end up giving us capital B over that derivative of that cx plus d, natural log of the denominator cx plus d. So the goal of this is we're going to have integral of some polynomial over polynomial, and we're going to use algebraic techniques to turn it into terms that are partial fractions of a constant over a linear, like they have right there. And then that is then integratable. So let's look at this first one. So it's still that one that they introduced above. We're going to have 8x plus 32 over x squared plus 3x minus 10. First step, we have to figure out what the factors are in the denominator. Got to figure out what those factors are. Those factors in the denominator are what will be the two new linear denominator factors. So our denominator, x squared plus 3x minus 10, it factors into x plus 5x minus 2. And so it should appear that we end up getting this, and that was created by using two fractions where these two things ended up multiplied, ended up being the common denominator. Those two factors ended up being the common denominator. So that means that we could write the new one as just make sure. Yeah. So that means we started off with 8x plus 32. And it factors into x plus 5 times x minus 2. So those new factors, those will be the denominators with some constant up above plus b over x plus x, no, that'll be a minus 2. Okay. And then we're going to have to find the a and the b, so I'm going to write this again over on the right side. 8x plus 32 over x plus 5, x minus 2. Sorry about the left-handedness. Again, that's capital A over x plus 5 plus capital B over x minus 2. So, first thing we're going to do now is on this one, I'm going to multiply everything by the x plus 5. Multiply everything by the x plus 5. When I multiply everything by the x plus 5, x plus 5's cancel here, and we're just left with 8x plus 32 over x minus 2. And when I multiply this by x plus 5, I'm just going to have a, and then this will end up being capital B, x plus 5 over x minus 2. Okay, then the next step, we are now going to let x equal negative 5. Let's let x equal negative 5. When x equals negative 5, this entire term will go to 0, and we will end up with a equals 8 times negative 5 plus 32 over negative 5 minus 2. 8 times negative 5, that'll be a negative 40. Negative 40 plus 32 will be a negative 40. Wait, why? Oh, I've been writing 32. It should be 82. I wonder I thought that was wrong. Okay. Should be an 8, 8, 8. Okay. Negative 40 plus 82. That's going to end up being a 42 over negative 7, which is negative 6. Okay, so we found the a. That's good. And then now on this side over here, again, that should have been an 8. On this side, we're going to find the b by multiplying everything by a x minus 2. So we're going to end up with 8x plus 82 over x plus 5 equals a times x minus 2 over x plus 5 plus b. And then similarly to the previous problem, I'm going to let x equal positive 2, because then when x is positive 2, that entire term goes to 0, and we'll just end up with 8 times 2 plus 82 over 2 plus 5. 8 times 2, that'll be 16. 16 plus 82, that'll be a 98. So 98 over 7. 98 over 7, which is 14, equaling b. So we have 14 for b, and we have negative 6 for a. Just making sure that's right. Okay, so that's, we found the b, which means that if we are wanting to integrate what we started with, integral of 8x plus 82 over x squared plus 3x minus 10 dx. That now became, since we found the a and we found the b, that now became negative 6 over x plus 5 plus 14 over x minus 2. And when we integrate this, this will now be negative 6 natural log of the denominator x plus 5. This should be absolute value. And then plus 14 natural log of the denominator x minus 2. Yeah. Let's see. And this is really just using straight algebra to figure out how we're going to split up the partial fractions, although it's also called, it says here, the Heaviside method, named by Oliver Heaviside. We go to the next page. There's actually a easier way to do this. I think it's easier, at least. So the idea here is that we're going to write the partial fractions with no numerators. Don't write the a and b. We're going to write the partial fractions with no numerators, and then we're going to cover up one of them. So if we cover up the x plus 5, then that's what it looks like there. So if we, with our finger, we're going to let x equals the negative 5. We're going to let x equal the negative 5. How am I getting the negative 5 and how I got the 2 on the other side is whatever makes that expression equal 0. It's whatever lets that expression equal 0. So this is quicker, less writing. In the left side, we're going to cover up the x plus 5, which ends up being that, and we're going to let x equal the negative 5. If we let x equal the negative 5 here, well, then similarly to what happened on the other side, we would get 8 times negative 5 plus 82 over negative 5 minus 2. So that ended up being 42 over negative 7, which was the negative 6. So that now gives us the number that goes above the x plus 5. So this answer, move that down there. There we go. Is now the numerator for the fraction with the denominator of the x plus 5. And then to find the other numerator, we're going to cover up the x minus 2. So covering up the x minus 2, it looks like that. So if we put our finger in the x plus 2 spot, like put our finger in that spot, and we let x equal the x equals 2. And we let x equal 2, what makes the x minus 2 0. And that gave us x at 8 times 2 plus 82 over 2 plus 5, which is then 98 over 7, which is 14, which is then the numerator that goes above the denominator of x minus 2. So a little quicker, less writing in that method. So let's try that with this example number 2. So first, we need to identify what the factors are going to be. Well, we have x minus 4 on top. Then we have x squared minus 6x plus 5. Well, it's going to have to be two things that multiply to get 5. It's only 5 and 1. And then they also have to combine to give us the negative 6. And so it's going to be minus 5 and minus 1. So we have x minus 5 and x minus 1. And so, trying the method that we discussed above, this will need to become a number constant over the x minus 5 plus another number constant over the x minus 1. So in what we discussed above, we're going to cover up one of the factors, and we're going to let x equal the number that would make that factor equal 0. So what would make the x minus 5 0? It would be 5. So I'm going to cover up the x minus 5 with my finger, and now I'm going to let x equal 5 in what's left over. 5 minus 4, that is 1. And 5 minus 1, that is 4. And so it might, I mean, if you want to like write this out to the side, if we covered up the x minus 5, if we covered up the x minus 5, we're going to have x minus 4 over x minus 1. And then if we let x equal the 5, that's then 5 minus 4 over 5 minus 1. And that gives us 1/4. So that is the constant that would go above the x minus 5 factor, 1/4. And then doing the same thing with the x minus 1 factor, if we covered the x up the x minus 1, we would be left with x minus 4 over x minus 5. And then we let x equal, what would make that term 0? What would make that term 0 is 1. So 1 minus 4 over 1 minus 5. 1 minus 4 is -3. 1 minus 5, that is -4. So just negative over negative will make it positive. So then 3/4 is the other constant. And then now to take the integral, the constant will be up front, 1/4 natural log of x minus 5 plus 3/4 natural log of x minus 1 plus c. So that shouldn't be too bad. Let's try that again on number 3. So how would this factor? Well, two things multiply to get -20 combined to get a -1. Well, that would have to be a -5, +4. So that means this is going to become integral of something over x minus 5 plus something over x plus 4 dx. So to figure out what those constants are, I shouldn't have written it like that first. I'm just going to write out the factors first. So we have 2 over x minus 5 times x plus 4 dx. There we go. And now that will end up equaling the integral of something over the x minus 5 plus something over the x plus 4 dx. So again, we're going to first cover up one of the factors, cover up the x minus 5, and we're going to let x equal what would make that 0. So we're going to let x equals 5 while we cover up the x minus 5. Well, I would plug the 5 into this one. 5 plus 4 is 9, so that will be 2/9. And then doing the same thing with this one. We're going to let x equal what would make that 0. What would make that 0 would be a -4. So I'm going to cover that up with my finger. -4 minus 5 would be, well, -9. 2 on top, so we have -2/9. And then to actually take the integral of that, we're going to end up with 2/9 natural log of x minus 5 minus 2/9 natural log of x plus 4 plus c. And now at this point, I want to make you aware of sometimes if you approach a partial fraction question that was on a multiple choice question, it would probably have the most simplified answer as the answer choice. And this is not the most simplified because we can use some natural log rules. And the reason we can't on this one, and it wasn't as easy to do so on other problems, is because we do have the same constant out front. We do have the same constant out front, so I can factor that constant out. If I factor that constant out of both, then I would be left with natural log of x minus 5 minus natural log of x plus 4. But when we subtract two natural log terms, that divides the arguments, that divides the insides. So this will become natural log of x minus 5 over x plus 4 plus c. Okay. Well, similar to how class normally works, I want to now give you a chance to do number 4 on your own. Try number 4 on your own. I'm going to stop sharing, and so you won't see me doing it. How much time do I have left? Ooh, only 12 minutes left in class. Let's go back to sharing and review what you should have gotten a little bit of. So that bottom, factor out x, I get x squared minus 4, and then that factors into x plus 2 and x minus 2. So that's what we have right there when we just factor the bottom. And then when you start doing the partial fractions, that means we're going to end up with a number over x. What's a number over the x plus 2? It's a number over the x minus 2. And then I'm going to cover up the x and plug 0 into all the x's, which will give me 12 over the 2 times the negative 2 when I plug 0 into those, which 12 over negative 4 is a negative 3. And then I would cover up that middle one, plug negative 2 into all x's, and when I do that, it would give me a negative 8 over 8, so negative 1. And then plug 2 When you cover up the x minus 2 and plug 2 into everything, that would be 2 times 2 plus 2, which will give you a 8 in the bottom. And when you plug 2 into the top, that will give you, what was it again? Yeah, that will give you a 40 on top. And so 40 over 8, that's going to give us 5 then. So that's what you should have gotten. And then that will end up equaling negative 3 natural log of x minus natural log of x plus 2 plus 5 natural log of x minus 2 plus c. Okay, number 5. So number 5, we have a higher degree in the numerator than in the denominator. We've already seen problems like this back on Friday. So we're going to do long division first, and then with the leftover one, we're then still going to have to do some partial fractions. So first, some long division. I'm going to have x squared minus 6x plus 5 cubed minus 9x squared plus 24x minus 17. How many times does x squared go into x cubed? X squared into x cubed will be x many times. X times all that. X times x squared will be x cubed. X times a negative 6x will be a negative 6x squared. X times b 5 will be a 5x. Okay, when we subtract all of that, x cubes go away. And negative 9x squared minus a negative, so that'll end up being plus. It's going to give us a negative 3x squared. And then 24x minus 5x will be 17x minus 17. And we could do it again. So how many times does x squared go into the negative 3x squared? Well, we'd have to multiply by negative 3. So negative 3. Negative 3 times that will be a negative 3x squared, as it should be. And then negative 3 times the negative 6x would be a positive 18x. Negative 3 times the positive 5 will be a negative 15. Okay, so those will cancel. 19x minus 18x would leave us with just a x. Negative 17 minus a negative 15, well, that's really a plus then. So that'll leave us with a 2. Negative 2. Okay, so there's the long division part, with x minus 2 being our remainder. So that means that this ends up equaling the answer at the top of x minus 3. And then we're going to have the plus the x minus 2, the remainder, over the denominator x squared minus 6x plus 1. And then when we take the integral of the x in the minus 3, that will not be too bad. But then this piece here, I'm just going to go ahead and get those answers. X squared over 2 minus 3x. Then this is going to have to be plus the integral of x minus 2 over, how does this factor? How does that factor? Well, that's going to be x minus 5, x minus 1. We did one like that before. Okay, and well, now similarly, this is going to have to be written as something over the x minus 5 plus something over the x minus 1. So I'm going to cover up the x minus 5 and plug 5 in. 5 minus 2 is 3, and 5 minus 1 is 4, so it'll be 3/4. cover up the x minus 1 and plug 1 in. 1 minus 2 would be negative 1, and 1 minus 4 would be negative 4. So a negative over negative, though, will cancel to be positive, so it'll be 1/4. And so then we have the x squared over 2 minus 3x plus natural log of 3/4 natural log of x minus 5 plus 4th natural log of x minus 1 plus c. If we get one more problem in, we for sure can be in 5th period. We have 5 minutes left. We can do one more of these. At least. So the idea with 6 and 7, they're both very similar. So I wasn't actually thinking that I would have time to do, that I would need to do both anyways. So what we're going to do here on 6, and the idea is also the same on 7. When we have problems like this, we would need to do both normal use substitution as well as partial fractions, such that if we have a problem of integral of e dx over e dx minus 1 times e dx plus 6, they already factor the bottom, which is nice of them. They didn't already factor the bottom on this one. So we factor the bottom on this one. If I factor cosine x out, that would be cosine of x times cosine plus 1. So it's going to be the same idea on both of these, though. If I'm going to do u substitution, then I also need to find my u. Well, du would then be e to the x dx, which is that whole piece there. So then this would end up becoming integral of 1 over u minus 1 and then u plus 6 du, not dx, du. So then, now we need some partial fractions. So it'll be something over u minus 1 plus something over u plus 6 du. So I'm going to cover up the u minus 1 and plug 1 in. Okay, when I do that, I get 1/7. I'm going to cover up the u plus 6 and plug negative 6 in. When I plug negative 6 minus 1 would be negative 7. So on the bottom, so it'll be negative 1/7. Okay, so now we have that. It would now become 1/7 natural log of u minus 1. And then minus 1/7 natural log of u plus 6. Okay, let's combine those. I'm gonna have a 1/7 out front. Natural log of, since we're subtracting, it'll become u minus 1 over u plus 6. And now let's plug u back in. So that will become 1/7 natural log of e to the x minus 1 over e to the x plus 6 plus c. And if you fall 7, it would be very similar to that. Now I'm going to go ahead and do 8. Sorry, 6th period. Running long in this video. Number 8. Well, we want the area under that function, which that is the integral from we are wanting the integral from 0 to 4 of 80 over, well, let's go ahead and factor that. How does that factor? We have x squared plus 6x plus 8. What multiplies to get 8 and combines to get 6? Well, that'd be 4 and 2. So we have x plus 4, x plus 2. Okay, well, then that's going to have to become the integral from 0 to 4 of something over x plus 4 plus something over x plus 2. So cover up the x plus 4 and plug negative 4 into the other stuff. So if I plug negative 4 into x plus 2, negative 4 plus 2 would become negative 2. And 40 over negative 2 would be, 80 over negative 2 would be negative 40. And then do the same thing here. Cover up the x plus 2 and then plug negative 2 in. Okay, so it's been 51 minutes. Plug negative 2 in. And then that would become a positive 2 right there. 80 over positive 2 would be a positive 40. Okay, so then we're going to have negative 40 natural log of x plus 4. And then we have plus 40 natural log of x plus 2, evaluated from 0 to 4. Okay, I'm going to simplify before I plug in the upper and lower limits. And what I mean by that is, with some of the other natural log rules that I've done ahead of time, I'm going to factor out the 40. It'll get multiplied by everything. And then this one has the negative, which means its argument is going to go in the denominator. So we're going to have the natural log of x plus 2 over x plus 4. That variable from 0 to 4. And now we'll plug the upper and lower limits in. So 40. We plug in the 4. That'll be natural log of 4 plus 2 is 6. And 4 plus 4 is 8. So it'll be natural log of 6 over 8, which is 3/4. Minus, plug the 0 in. We plug in 0, well, that'd be natural log of 1/2. And we can again simplify to get 40 is natural log of 3/4 over 1/2. And, well, you got a fraction divided by a fraction. 3/4 divided by 1/2 would mean times 2, because you multiply by the reciprocal. And so that would be, we can just have a 2 on the bottom, so it's just 40 natural log of 3/2. That's right, plus C, that's not necessary. It's a definite integration problem. We found the exact answer for the area under that function. Okay, then number 9 would be very similar. We'll probably go over number 10, beginning of tomorrow's lesson, as well as do a partial fractions normal at the beginning of tomorrow's lesson. Again, I wish I could be there. And I will see you next Monday. Have a good day.